So I was looking at some videos on YouTube, some cool math videos, and I ran across something like this. Here's a sequence of numbers. Find out what the next number is, or find out what the 12th number is in this sequence. What they said was, okay, this sequence is what's called a quadratic sequence. Well, in high school, I learned all about arithmetic sequences where you add a common difference each time to a starting point number. And I also learned about geometric sequences where you multiply a starting point by a set number each time. They call that the common ratio. But I wasn't really too familiar with quadratic sequences. And what they said was that a quadratic sequence follows this pattern. An squared plus bn plus c is the element for the nth element. And so a, b, and c are set coefficients, and n varies like this: 1, 2, 3, 4, 5, and so on. Okay, and then of course on the homework or the test, they would ask you, given this sequence, find the 12th term of the sequence. So the way that it was presented on the video was what I call a recipe approach. In other words, it's a step-by-step method of finding the answer. Now, the method that you're going to see here will seem fairly artificial, and I'll just let you know that the rationale behind all of this will be seen real clearly in the part 2 video on this series. So here it is. We start with this sequence, and I'm using a particular one here. There were all kinds of different sequences, but anyway, we'll start with this one: 5, 11, 23, 41, and 65. The first step is to find what's called the first difference. What does that mean? Well, what you do is you say 11 minus 5, and you get 6. Okay, the next one you would do 23 minus 11. Can you figure that one out? Indeed, it is 12. And then we continue that with all of the numbers. 41 minus 23 is 18. 65 minus 41 is 24. Okay, that's nice. Now, they then say take a second difference. And what that looks like is, well, 12 minus 6, that will be 6. And 18 minus 12 will also be 6. And 24 minus 18 will also be 6. That's interesting. In fact, it turns out that because that second difference is a constant number, that means that this is a quadratic sequence. So given all of that, let's start building the quadratic so that we can find our elements in the sequence. So we start off with this idea. So we want to find A, B, and C. So the first step is very simply take half of the value of the second difference, and that will be your A value. Again, the reasons why you'll see in the next video, but let's just go with it. So in our case, the second difference was 6, so A is going to be 3. And now with just the A equal 3 and not the B term and the C term, we will generate the first 5 terms of the sequence. In other words, 3 times 1 squared, 3 times 2 squared, 3 times 3 squared, 3 times 4 squared, and 3 times 5 squared. And when you do that computation, you get 3, 12, 27, 48, and 75. So now let's figure out the ending. In other words, these two terms here. Okay, take the new sequence that we just generated at the end of the last slide and compare it to the original sequence. Okay, here's what we just generated, and here's the original sequence. Now we asked the question, what would it take to go from the first term of that new sequence, starting with 3, and getting to the original sequence? So to get from 3 to 5, what do? Well, you would have to add 2. But now to go from 12 to 11, you have to subtract 1, and so forth. And when you work all of those out, you get this sequence of numbers: plus 2, minus 1, minus 4, minus 7, and minus 10. Well, if you look at that, you'll notice that there is a common difference of -3 each time. In other words, to go from 2 to -1, you have to subtract 3. Likewise, with -1, you subtract 3 and you get to -4, and so on to -7 and to -10. So the common difference here on this sequence is -3. So that's what B is going to be equal to. Again, why is that true? Wait for the next video. Now, since we have A and B, we can compute C by simply plugging in and saying that 3 times, and we'll use the first term because you could use any of the terms in the original sequence, but we'll use the first one because using 1 is an easy one to compute. So 3 times 1 squared plus -3, that's B, times 1 plus C, which we don't know yet, is equal to, the first term in our sequence was 5. So that means that 0, the 0 comes from 3 times 1 squared is 3, and then -3 times 1 is -3. 3 plus -3 is 0. 0 plus C is equal to 5. Thus, C is equal to 5. So we've got all 3 of our coefficients, A, B, and C. And so now we can check the solution to see if it is correct. So here we have the whole quadratic. S sub n is equal to 3n squared minus 3n plus 5. And when you do the computation with a calculator or a spreadsheet, you can easily see that the 5, 11, 23, and 41 and 65 are indeed the original sequence. And then if they ask you, okay, well, tell me what the 12th sequence or 12th element of the sequence is, you simply plug in 12 for n, and in this case, I got 401. So if they ask you, whatever number, then you can just simply plug that in. So let's use our recipe and bake another cake. Here's another sequence. Let's see if we can figure this out. And we'll leave out a lot of the explanation. We'll just do the steps. Okay, first, here's the first difference. Here's the second difference. Oh boy, we've got a quadratic. Take half of that, and we get A is equal to 1. Okay, so we write down the A equal 1 sequence. 1 times 1 squared plus 1 times 2 squared. And I'm sorry, I shouldn't say plus. So 1 times 2 squared, 1 times 3 squared, 1 times 4 squared, 1 times 5 squared, and so on. We write down the original sequence and we ask the question, what does it take to go from 1 to 4, and from 4 to 13, and from 9 to 24, and so forth, and we get this sequence here: 3, 9, 15, 21, 27. And if you notice that there's a common difference there of 6. So that's our B value. And so we plug that in for the first element of the sequence, 1 times 1 squared plus 6 times 1 plus C is equal to 4. The 4 is there because that's the first element of the original sequence. Then doing a little computation there, we say 1 plus 1 squared, that's 1, plus 6 times 1, that's 6. 1 plus 6 is 7. 7 plus C is equal to 4, and so therefore C must be equal to -3. So let's check and make sure that that's correct. We plug it in to a calculator or spreadsheet, and we find that indeed our values match the original sequence. And then if they come along and they ask you, well, what is the 20th value of that sequence? You can simply plug in 20 for n and get, in this case, 517. So that's it. And then you can try some other quadratic sequences and see if it works for you. So my assessment of this method is this. The rote process, or the recipe way of doing things, seems to work just fine. However, you've got to go through all of the steps for every sequence. And there's always the chance for making computational errors when you do lots of arithmetic. So that could be a drawback. So for the next video, little preview, what we'll do is we'll look at a more direct method that will have many fewer steps. However, there will be some algebra involved to get a derived formula. See you next time.